Well, good afternoon, everyone, and a very warm welcome to this Dimensions programme Engage and Inspire event. Thank you very much indeed for joining us this afternoon. As Deputy Principal of Van Mildert College, this is a particularly special event for us this afternoon, and our speaker is somebody that we know very well. Professor David Harper is Principal of Van Mildert College and Professor of Paleontology in the Department of Earth Sciences here at Durham University. And he's been Principal of Van Mildert College for 10 years. He'll retire from that role this summer, so this is actually Dave's final lecture as Principal of our college. We're really looking forward this afternoon to hearing about Dave's many fieldwork adventures, and with that I'd like to hand over to our Dimensions Programme Scholar, who's Christy Chung this afternoon, to provide the introduction. Thank you, Christy.
Hi everyone, welcome to today's event. Joining us today, we have someone who I'm sure is a familiar face to most, Professor Dave Harper, Principal of Van Mildert College. Dave Harper is a leading international expert on paleontology and the fossil record. He is a Professor of Paleontology, Principal of Van Mildert College at Durham University, and Chair of the International Commission for Stratigraphy, an extensive global network of leading experts tasked with reconstructing the history of the Earth. He's a former president of the International Paleontological Association and the Paleontological Association. Dave began his teaching career in University College Galway before moving to a professorship in Copenhagen in 1998. He has published over 350 scientific articles with over 40,000 citations, 15 books and monographs, including several influential textbooks, and collaboratively developed the widely used software package PAST. Dave's research programs have taken him to many parts of the world, including Australia, Chile, China, Greenland, Russia, Scandinavia, and Tibet. His research has been recognized by foreign memberships of the Royal Danish Academy of Sciences and Letters, the Royal Swedish Physiographic Society, and an Einstein Professorship in the Chinese Academy of Sciences. A really warm welcome to Dave. We're sure that this will be a fantastic evening for everyone. We've got times for questions at the end, but if you've got questions, please feel free to pop them into the chat during the session. And now passing over to Dave.
Okay, well, thanks very much, Christy, for that wonderful introduction, and thanks too for Vicky. Yes, I'll have fulfilled my 10 years at the end of September, and like all retiring principals, I'll be moving on and engaging more fully, I hope, with some of my research interests and some of the problems I've been trying to solve over very many years. This was a great opportunity I had when I was in Copenhagen, and at that particular time in the late 2000s, there was the possibility through the Danish Innovation Center in Shanghai to do some joint projects with Chinese colleagues. A lot of the money was going to fairly trendy sources, I would say, like molecular biology, genetics, those sorts of things, very important areas of science. But I got together with a colleague and thought, well, perhaps we could come up with something rather spectacular in the geological sciences and get some funding for that. Now, I've got very strong links, as many people know, with the Chinese Academy of Sciences, particularly colleagues in Nanjing. And it was possible to put forward a program to think about what's on top of Everest, really, and try and get into Tibet and study some of these sections again. And we were very fortunate to do that. It being invited to give this talk, and I was absolutely delighted with the invitation. I was asked perhaps to extend it a little bit and cover a few anecdotes of other areas of the world that I've investigated over the years. I'm going to do that very briefly and touch on some general themes within my research areas. So one on top of Everest, we'll come to that a little bit later, but I want to start with this mountain here. which I've looked at many mountain ranges. I've collected fossils from many mountain ranges, but I still return to this being the most beautiful and wonderful of all the mountains, and that's Sylvan in the Northwest Highlands of Scotland. For those of you that are acquainted with geology in this part of Scotland, the low ground here, these sort of rolling hills, are occupied by what we call Lewisian gneisses. They're very old. They're about 3 to 2 billion years old. They don't have any fossils. They're metamorphic rocks and some igneous rocks. They've been tectonized, deformed, those sorts of things. But sitting on top of Sylvan, and Sylvan is one of a series of these monodocs that are sitting on top of the Lewisian gneiss, what Ben Peach and John Horn, who mapped in the late 1800s, used to call the old boy. And sitting on top of the old boy was this succession of red conglomerates, of sandstones, almost horizontal in places, and occupying this whole area across the wonderful landscapes of the Northwest Highlands. There are actually fossils. These successions are over 1 billion years old, but palynologists who have been working on some of the traces of early plant life are beginning to discover some quite spectacular fossils within some of the more shaly bands, and reconstructing plant and some animal evolution in the latter part of the Precambrian. If we're going to talk about fossils and mountains, we really have to talk about Rudolf Trumpy as one of the great alpine geologists. He was actually born and brought up in Glarus in Switzerland. I'll come back to that a little bit later. But Rudolf Trumpy sorted out a lot of the structure of the Alps through detailed mapping, but he had a great respect for fossils. And he famously quoted, "One bad fossil is worth a good working hypothesis," which meant, you know, you could be mapping a whole nap, a whole terrain, a thrust sheet, and suddenly you find a fossil that totally changes your interpretation of the age and the origin of these thrust sheets. Fossils in fold belts are generally rare. They're often deformed, but they are very, very important. And going back a bit, in 1991, myself and a colleague from Oslo, David Bruton, we organized a conference, a symposium in Strasbourg in the days of the EUG, the European Union of Geosciences. And it was precisely on fossils and fold belts. And we had a full day of some wonderful presentations on fossils from the Alps, from the Caledonian mountain chain, the Appalachians, the Frisken belt, those sorts of places, showing just how important fossils were in reconstructing Earth history. At the end of a day of fantastic presentations, a rather distinguished gentleman stood up in the audience. The room went a little bit quiet. People started looking around, and this gentleman said, "Well, somebody once said, one bad fossil is worth a good working hypothesis." And my colleague said, "Well, you obviously didn't attend the start of the symposium. I actually said that." And the room went even quieter. And somebody leant over from the first row and said, "Did you know that's Rudy Trumpy?" Well, we didn't, and we apologized afterwards, and we had a very good chat. The Glarus thrust, and Glarus, where Rudy came from, is quite a remarkable section here, because again, we've got a succession of rocks, except on the bottom, we don't actually have the oldest rocks, we have the youngest rocks, and these are Jurassic to Cretaceous in age, part of the ultra-Helvetic Nap sequence in the Swiss Alps. And on the top, we have Permian, possibly Triassic conglomerates of the Veracano succession. And quite clearly, they've been thrust over these younger rocks. And this was quite revolutionary in that it demonstrated that not only could mountains go up and down, which probably we knew already, but also there were large-scale horizontal movements in the Earth's crust. And again, fossil played a very important part in identifying the components of these thrust sheets. So fossils can tell us the relative ages of the rocks, and they can tell us where on the globe they originated, because every fossil, every plant and animal has a distribution. They occur in different provinces across the latitudes, and so they're very helpful in telling us where things are. And for people that are non-geologists, which probably most of you, a little bit of background, two things. Firstly, about space, about place. The globe is covered by tectonic plates, and these are all moving around. Sometimes they move apart, and lava comes up and continues to build our oceans, and the fresh lava solidifies and sticks onto the plates as they move apart. And a classic example, of course, is Iceland. And Iceland is sitting here on the mid-oceanic ridge, North American plate moving that way, Eurasian plate moving this way. And then we have these incredible volcanic terrains in Iceland with the lava fields here, various cones here, and a very tectonically and magmatically active part of the Earth's crust. But when the continents actually collide, and a classic example is the African plate with the Eurasian plate, and the Indian plate with the Eurasian plate, and I'll come back to that a little bit later, they form mountain ranges. And here we are in the Austrian Alps. I'm trying to look quite dignified here in the blue fleece, having spent over 3 hours climbing up this valley to the top, so completely out of breath, but now looking at some of the fantastic Devonian and Carboniferous limestone sequences stood up on their end in this part of the Austrian Alps, and the Alpine belt originating from the collision of these two continents. Now, where do the different parts of mountain belts come from, and how can we tie continents together in deep time? Well, fossils, and I mentioned before, they occur in provinces generally. We can start looking at the distributions of animals and plants and fit together the continents. And this is a classic example that's in all the textbooks, including Benton and Harper, in which we can see towards the end of the Paleozoic, the early Mesozoic, Africa, South America, India, Antarctica, and Australia were all more or less fused together. And how do we know that? Well, we can look at the distributions of some of the key fossils. And this pig-like rhynchosaur, Lystrosaurus, occurs right across these various belts. We have the freshwater Mesosaurus that links South Africa to South America, and the very famous Glossopteris, which Scott found on his ill-fated expedition to Antarctica, stretching right from Australia to South America. So provinciality, paleontology, fossils, absolutely essential in trying to reconstruct some of these plate configurations through deep time. And of course, it's become really sophisticated now, and this is work by Robin Cox based on his research with Trond Torsvik in putting together some of the paleocontinents during the Ordovician. And as you can see, based on paleomag and faunal evidence, you can start to build up a very detailed picture of the globe, in this case, 450 million years ago. And this was work done a number of years ago by one of my Danish PhD students, Maria Lilleroot, and she started to actually fix some of these circulation patterns around the continents to try and understand the migrations of groups of fossils, groups of invertebrates such as the Brachiopods, the trilobites, and the graptolites. I'm going to show you this diagram because this is the time element in the talk, and we've sort of covered a little bit about space and moving around continental plates and why fossils are important. This is a little bit more about the time dimension and why they're pretty good for helping us date rock successions. We know on the planet life has been around for a long time, origin of Earth here about 4.6 billion years. And then by about 3.8 billion years, these are some of the rocks in the Isua complex in West Greenland, which my former colleague Monique Rosing studied and found a biological signature in the carbon isotopes, which suggested that life was already there in some profusion 3.8 billion years ago. Stromatolites, these sheets of calcium carbonate stuck onto cyanobacteria, were very common throughout much of geological time. And then the larger organisms, the Ediacara biota, come in later in the what we call the Proterozoic, about 600, 680 million years. And then the area I'm particularly interested in is right at the base of what we call the Phanerozoic here, from about 540 million years onwards. Two systems of rocks that we call the Cambrian and the Ordovician, and they're dominated by skeletal organisms, such as Brachiopods here, which is the group I work on, and lots of other really exciting fossils. I think we have to bear in mind, and one of the other reasons I show this diagram is really the sort of the deep time concept of life and its origin and its diversity today. Sometime way back in the Precambrian, way back probably about 4 billion years, there was probably one prokaryote cell. And then that multiplied into the great seas of cyanobacteria, their products, the stromatolites, the material that's stuck onto their mats, and up to the present day, where we have, as a very, very conservative estimate, 20 million eukaryotes, complex animals living on the planet today, and that's not counting the very simple unicellular organisms lacking a nucleus and those sorts of things. So an incredible history of life. But the important thing is that life evolves, species go extinct, species originate, and different sorts of organisms tend to characterize different intervals in geological time. So by looking at a species of ammonite, for example, or a species of trilobite, we can tell where we are in, say, the Jurassic with the ammonite, or the trilobite, where we are within the Cambrian. So they're very good at telling us relative time. Okay, I'm going to start with the Cambrian explosion and talk a little bit about where I spent very many years when I was in Copenhagen every summer, going to different parts of Greenland to do different pieces of field work and leading many of the expeditions there, which was really good fun. And the Cambrian explosion is really right at the base of the Cambrian when skeletal life bursts into its full glory. Some people have called it the carnival of the animals. But some of the field experiences were really quite amazing. This was our first field season in Sirius Passet. And this is JB Cox Fjord here. This is the wonderful terrain. I think our camp was somewhere down here by the fjord here, and then walking up into the mountains every day. The white limestones are pretty old, they're Precambrian, but the darker strata here, the darker rocks here are Cambrian in age, and they're yielding this fantastic fauna that is part of the Cambrian explosion. When I was planning the expedition, we talked a lot about where we could land, and there was an airstrip there very many years ago, in the 1980s, it had been used by the Geological Survey of Greenland on its expeditions, but we weren't quite sure of the state of that airstrip anymore. We talked to the pilots and persuaded them that we should give it a go. It would mean that we were pretty close to the camp and not too far away from the exposures. So basically, we got up there, we flew over the mountains from Station Nord, and the Twin Otter pilots had a look at the ground. They weren't very enthusiastic about landing. They did quite a few circuits off the fjord. I was sort of in communication with them. All the red lights were flashing on their dashboard, and a Canadian voice was saying, "Stall, stall, stall." And one of them said, "Don't worry about it. We know what this aircraft does." And so they circled quite a few times, and eventually they put it down, and we stopped with a hell of a bump. And one of the pilots turned to me and said, "You know something, unless you repair this airstrip, we ain't coming back." We did that. Every evening we went out and we filled in all the holes, and it was really like the airport in Copenhagen, Kastrup, by the time we'd finished. It was absolutely perfect. So when the pilots came back, they were different pilots. They didn't really know what the problem was. Okay, so out of these rocks, we've collected over 50 different species of quite amazing animals. They tell us that we're in the lower Cambrian. We knew that already. And they are associated with the tropics. They're very similar to faunas from the Burgess Shale, from Chenjiang, those sorts of places. And that was really what we set out to do. And we're continuing to work on these. We've got some fantastic models of these fossils, and they are quite remarkable animals. We've been able to reconstruct the ecosystem at the time, and it was quite a diverse ecosystem with a lot of food in the food chain. So there was a lot happening straight from the word go in the early part of the Cambrian. The other area that I've spent a lot of my life on is the Great Ordovician biodiversification, and that came a little bit later. And this is where species, this is where families, genera, those sorts of things really diversified a little bit after the Cambrian into the Ordovician. And I'm going to go and have a look at some of the localities that we went to there to chase this up. I'm setting a bit of background here to build up to why this is important in looking at Everest. This is Peters Quarry in the St. Petersburg district. And here's some of my, again, former students from Copenhagen, Christian, and this is Arna, who's on the staff there. And we spent many weeks in Peters Quarry with Russian colleagues. It's not the best place in the world to camp. There isn't fresh water. My students did complain about that. And one of the van drivers said, why do you need fresh water? We have cases and cases of vodka here. But I think, they just basically wanted to wash and, keep clean. We collected 30,000 brachiopod fossils, and these are the guys here. And we built up an indication of a diversity profile here. And so within the Darwinian, this interval here, which I'll mention again, very rich 50-odd species. And this seemed to be associated with isotopes, and I won't go into great detail, but oxygen isotopes, which suggested that the water was cool at the time. And so this diversification seemed to coincide with a cooling of the waters. Well, let's go back to Greenland and let's look at the Ordovician this time. And this is one of the most spectacular parts of Greenland. It's the northeast Greenland. It's the fjord region there. It's pretty well accessible by Twin Otter coming out of Constable Punt or Mestersvig, some of the bases in the southern part of Greenland. Here we have a great succession of Precambrian rock, those of you that know a bit about the Precambrian, this covers the interval of snowball Earth, these succession of tillites here. And up here in the distance, high in the plateau, we have Ordovician rocks. We started working on the Cambrian here, and we were looking for a serious passat type of fauna, a Cambrian explosion fauna, but we've not been successful in doing that. We found lots of other things. But this is the Ordovician here and here, which was a real target for a lot of our exploits. We were able to get a helicopter every so often, but the helicopters tend to charge by the minute, so it was a bit of a luxury. But nevertheless, we moved on in subsequent field seasons to go much farther north, and this is around the 83 degree latitude, which is probably about as far as you can get in Greenland before you come to the North Pole. And this is Citronen's fjord area, where we collected some fantastic fossils. But again, in part of this operation, we had to use both the twin otter and the helicopter. Some places were a little bit inaccessible. And I think I've told this story before. The helicopter that we were meant to use about a couple of days before we arrived had got into a bit of a snowfield on a ledge. The pilot thought the ledge was solid, but the helicopter fell off the ledge and broke off the rotor. So a new helicopter had to be requisitioned from Montreal, which took a few days to arrive. So we had been using the twin otter, which was rather interesting, because twin otter pilots tend to have competitions as to the least amount of meters that it takes to take off. And these guys, Chris and Jim, were landing and taking off in about 60 meters, which sounds absolutely impossible. But they did it. Small sandbars they were landing on and taking off from to get us down there. This is often known as convict rock because of the sort of arrow shape of these particular fossils, but they're very sort of robust fossils that indicated that we were in the late Ordovician, which we didn't really know before in this part of North Greenland. We've looked at Ordovician rocks in other parts of the world, and one of the more exciting areas I've looked at has been with Russian colleagues in parts of Siberia, Arctic Siberia. And in this case, we would meet in Moscow, fly to Krasnoyarsk, and go to a little town called Bykit. They managed to get me into this Hind helicopter, which tends to take off in a vertical direction, and then at a certain height, then readjusts itself and starts moving forward. It dropped us off right in the middle of the Siberian forests, by the side of this rather large river. And our job over the next 2 or 3 weeks was to stop off at various parts and examine the Ordovician successions, and hopefully end up back in Bykit and return by more normal transport. Fantastic amounts of information. This person with his back to us, I think, is Igor, who was one of our field assistants, and his job was to catch fish every day. So during the expedition, which was rather nice, we had either smoked fish or fried fish or fish soup or poached fish, or whole varieties of fish, and it was really fish soup, and it was really wonderful and thoroughly enjoyable. Australia was a little bit different. Again, we were chasing the Ordovician. Everything was red. The sunsets, the dawns, the rocks, the ground. But the challenges were very different from rubber boats. They were this field vehicle here, in which it was very difficult to get moving. We were always getting caught in creeks and having to pull it off. At the end of the expedition, we were a few 100 kilometers away from Ayers Rock, and we looked at each other and said, Ayers Rock, It's a tourist attraction. Well, maybe we should go. And so we ended the expedition here in Ayers Rock. But along the way, all sorts of incredible creatures, spiders that we had to be very careful about. I had a bat in my tent one night, which wasn't a very welcome sleeping companion. I managed to flush it out eventually. Camels were being herded across this whole region, and marvelous Ordovician rocks, again, around the time of the Ordovician biodiversification. Our work in China, I've done a lot of work in China since the 1980s, and this was a very interesting expedition again to look at Ordovician rocks. We started off in the Taklamakan Desert, and with various types of transport that I wasn't too happy about. This one was quite incredible. I'm looking a little bit shocked. You can see the background here. We'd just been right over that with hundreds of meters of drop on this chairlift. But the rock successions in the Tarim Basin, the Tarim Marginal Belt, were absolutely superb through this Middle Ordovician succession. And finally, in this little part of the show, showing you a few vignettes of Ordovician geology, the Anti-Atlas Mountains, the Feswata fauna, which is a little bit like the Cambrian Explosion fauna because it is exceptionally preserved. But again, we're out in the desert. And I just wanted to make a little point here because it's all about international networks. It's all about collaborating with colleagues across the globe to visit these sections, to work on big joint projects together. And I think there's about 6 different nationalities in this particular photograph. But I would mention my wife Maureen here, and incredible support for my career over the last 40 years. And I wouldn't have been able to take these trips and go to all these amazing places without her support. And sometimes you just go to a place and it's a complete and utter bust. It doesn't work out. And that's what happened in the Andes. We did have funding. We were part of a bigger project. We spent many weeks in this gorge, which was hot as hell, being observed by the animals, trying to find Ordovician fossils. We found hundreds of examples of a worm-like creature. We still don't know what it is, but we never really found the key fossils of the Ordovician biodiversification event. Realizing it was a complete bust, we took off and tried to find localities elsewhere. We had a few wonderful days in the Atacama Desert camping, which the skies were absolutely wonderful. Well, you're wondering when we're going to get to the Himalayas. Well, here we are now. And the Himalayas is situated in the Tibetan Plateau. It's an extremely large area. Some people call it the third pole in the world. Average elevation height of about 4.5 kilometers. And really what we're interested in is this belt of rock here, which is the part of the Everest range along here. We've got Everest here, Nualam here, where we stayed for some of the time, and the successions on the top of Everest that really had sort of fascinated me for quite a long time. We started our journey in Qinghai, in the Nationalities University in Qinghai, and we had many great experiences with these the culture of the region. And this is one of my Danish colleagues, a zoologist, playing with one of these prayer drums, which you can turn around and say your prayers to. But we got on this incredible feat of engineering, which is the railway from Qinghai up to Lhasa. It's my colleague Lars who decided that maybe he should read up a little bit about where we're going. And we crossed some remarkable terrains, the headwaters of some of the major rivers in India, the Ganges, for example, here. and then to reach eventually Lhasa and into the Himalayas and off the train. The wonderful architecture of the Potala Palace here, the seat of the Dalai Lama, who has long since gone. Wonderful hospitality and food, and heading off to what is a nightclub. My colleague Lars turned out to be an extremely good dancer, and was much admired by the dancing troupe here. I realized very quickly that yak milk and yogurt is really nice. Yak tea isn't really very nice. And one thing that I did also realize was you shouldn't actually empty your cup. I didn't really like it. I thought, well, I'll just drink it and maybe get a soft drink. But that was very impolite, because they rushed over our hosts and filled it up again. And so that was that. We headed up there. These were our field vehicles here. The drive was really hairy, up and up and up. The drivers tended to say a little prayer before they got into the cabs, and then took us on to the next part of the journey. These were pretty prominent along our journey. I think we were getting up to about 5 kilometers here. And these are the prayer flags with various prayers written on them. And the idea is that the prayers will blow into the wind. I think at that stage, where none of us were feeling too well, our hosts mentioned a little bit about Tibetan burial. And basically, the bodies are taken out and laid on the top of mountains for other animals to benefit from the corpses. We visited quite a number of temples, and these are the pupils and the monks, and they basically just repeat and repeat and repeat their lessons. And so they learn by rote, whether it's mathematics, whether it's physics, whether it's history. It's all done by chanting and repetition. And these are the famous yaks, which are used for a multiplicity of purposes. Where we went and where there were populations, and these are the kids of farmers, yak farmers, they were very curious and extremely friendly. This is the group that tackled the Everest range, and this was our guide and general translator. These are the geologists that I've worked with for many years before. Zan Ren Bin, who's now director of the institute, the Chinese Academy of Sciences Institute in Nanjing. Jianbo Liu, who's now director of education in Peking University, and Lars Stemmerik here, Danish colleague, who was the head of the Geological Institute in Copenhagen. And the others are mainly zoologists that were there to have a look at the living fauna. This was our target, right in the very top. And quite clearly, you've all realized that we weren't going to climb up there, because basically we couldn't climb up there. So the actual field area that we're diving into is this area around Nualam. Looking at it in a little bit more detail, Jayakun, we had information that this section here was very similar to the section on the top of Everest. We were up in pretty spectacular scenery. It was around heading up to 5,000 meters, 5 kilometers. We had to walk very slowly. I did get headaches, occasional hallucinations, being covered by spiders and things like that. But once we got used to it, after a couple of days, it was pretty good, but nothing too strenuous. Everything was done at a very, very slow pace. This is a map that we took from Google Earth before we went joined our Chinese colleagues. And these are the sections on what's known as the Friendship Highway. And the Friendship Highway runs, I think, essentially from Beijing right into Nepal. But the sections were very conveniently located along this highway. And so we were able to access these data quite easily. Now, we knew initial reports in the 1930s from mountaineers had brought back rock samples, and some of them are in Oxford University. And the summit of Everest was considered to be much younger than we know today, Carboniferous or Permian in age, with crinoids. And I'll come back to crinoids a little bit later. Very fortunately, the rocks swing round and crop out at much lower altitudes. And so next to the Friendship Highway, we can examine these exposures. This is the yellow band, which is just near the top of Everest, and above it is the limestone band that we're most interested in. The Chinese Academy of Sciences had been very active in the area in the 1960s. They published a lot of studies in Chinese, and they suggested first that these rocks were in fact Ordovician in age. And so we had a lot of literature to build on to try and see the significance of this age and the significance of the rock facies. This is work done in the region by largely an American group, Paul Myro in Colorado, Nigel Hughes in Riverside, and they'd built up this schematic sort of section, and they'd worked in a lot of other areas in the Himalaya, in India, and they had recently moved into Tibet, but they were much more interested in the Cambrian rocks, the older rocks, rather than the actual Ordovician. Here is the yellow band that I mentioned before, and these are the limestones, which geologists would call the Chiatsun group at the top. This is our field area, and these are some of the key localities. This is where we got most of the brachiopod fauna from. And conadonts and crinoids, I'll mention a little bit later, came from here. Jambo is a sedimentologist from Peking University, and he and Lars Stemmerik measured the sections and worked out the sorts of environments that existed back in the Ordovician in this part of the world. And this is some geological logs with limestones and dolomites, particular rock types, but they would suggest fairly shallow water types of environments with a lot of bioclastic material, which is fragments of the skeletons of organisms, peritidal dolomites, some evaporites, pretty shallow water in this part of the cycle. And they've identified quite a number of different facies. And if we look at it closely, it's what we call biotibated, which means animals have been working their way through the sediment, digging burrows, munching the sediment, walking or moving through the sediment in that particular way. So there's a lot of activity there in these Ordovician rocks. And two of the key fossil groups that we found are firstly a microscopic group, and these are called conadonts, and they're really good for telling the age of a rock because they evolve very rapidly and they're quite easy to identify. And these are parts of the mouth apparatus of these rather nasty looking creatures called the conadonts, perhaps related to lampreys and hagfish today, but they were these slim, and they tend to just fasten themselves onto the side of larger organisms and possibly suck out the contents of these. And so these are bits of the feeding apparatus in here of the conadont. And these are stems of crinoids. We often call them the sea lilies, and I'll show you a picture of those a little bit later. So we've established pretty clearly that these are Ordovician. They're very precisely within the Darawillian, which is a time interval within the Ordovician. And also we can tell a little bit more about the environment of this particular unit. And so this is Jan Bo's reconstruction, that we're probably in this part of the sequence in a more shallow subtidal area. We're on the shelf. The brachiopods was my main interest, and Zanren Bin too is a brachiopodologist, and we spent a bit of time on this succession here collecting brachiopod faunas. Very rich fauna, very diverse, and very well preserved, which meant we could identify the species of these brachiopods. And here we are in the process. These were put into acid often to get the actual molds out, so we could see the internal features a lot better. Again, this is another time chart, the Darawillian. We've been talking about the Ordovician, so the Darawillian is in the middle part of the Ordovician. We had previously worked on very similar brachiopods from South China, and we have a very good age for those. And we'd also done some multivariate analysis, here's some cluster analysis, so we can look at the different localities, the different faunas, and on the basis of the species that are present, we can cluster those areas that have species in common together. And we can see we've got a low latitude area here, and Wudang is essentially this area here that we worked on in South China. That's very similar to some of the fossils around North America at that particular time, and parts of Western Norway that would have been part of North America, quite different from the high latitude faunas of the Baltic, of Morocco, of the Czech Republic, of those sorts of places, and Wales here. We can then go into a lot more detail, having spent a bit of time looking at all the different species, and we were able to assign our brachiopods to what's known as the Tokima tablehead province and the Aporthophyla group, using principal component analysis now on the same data sets, but still retaining our cluster analysis, which again confirmed these two different groups of brachiopods. And again, we published the full story recently on the Conadonts from these horizons. So what does it all mean? Okay, well, we got a pretty good age, very precise age, and we're also, you know, we got India down here, and the Tibet fauna here. This is a diagram I produced with a lot of different colleagues in 2013. Looking at the world during the Middle Ordovician, which is the Darawillian, the area we're interested in. And this is looking at these various terrains and how they might slot into the various provinces that were around at the time. We can see we've got a low latitude province with stretching from North America through Siberia. These are areas I've looked at myself. South China, and then onto Australia again. And a lot of these data we picked up through these field campaigns that I've been discussing with you earlier. There are the Celtic provinces, which is more typical of the higher latitudes of England and Wales, and those sorts of areas, which pops up across here and here. But generally, we're looking at the Tibet being marginal to this low latitude province, and along the margin here we have what's known as the Tokima tablehead realm, which includes Western Norway, parts of North America, and parts of South China, and those sorts of things. So here we are. This is the north face of Everest, and what have we learned from a very exciting month in Tibet? Well, it is capped by marine limestones. These are and that's been known for quite a long time. What we now know, and what the Chinese colleagues discovered in the 60s, early 70s, is it is Ordovician age. It's not Carboniferous, it's not Permian. What we've added to the story, they are tropical marine limestones, largely. They're a long way away from where they were deposited, and they're now right up there on the roof of the world. This is a more up-to-date map, I think, by myself and Maria, and we can more confidently plot on Tibet here, right on the southern margin of this low latitude province, and that would make a lot of sense within this Takema tablehead realm. This is very good because it actually confirms quite a lot of work done by Trond Torsvik and Robin Cox and others using paleomagnetic data. And so looking at the paleomagnetic signature, you can place continents roughly around the globe. Very good on latitude, but not so good on longitude. And here we have Tibet on this. We're just within the tropics here, and we're not in huge disagreement on this. And so we can summarize by saying that this rich shelly fauna is of Dirawillian age. It's 460 million years old. It occurred in a range of subtidal environments. They're linked to tropical assemblages, the Takema tablehead province. And a thing I didn't mention was that they seem to be linked to what we call in geology a transgression, a major rise in sea level. And how did it all happen? Well, I think we can link it into the paleotectonic environment and plate movements of the time. And it's very well documented that India has moved a considerable distance from 70 million years to the present day with its collision with the Eurasian plate to form a mountain belt, as I talked many minutes earlier. It collided there, and in the meantime had swept up this Ordovician terrain that many millions of years earlier had actually been deposited in an ocean in the tropics during the mid-Ordovician. And that links in really to what I started to talk about on the Great Ordovician biodiversification. It is another piece in the jigsaw puzzle for us in tracking all the localities around the globe, giving us new pieces of information about this largest radiation of marine life in Earth history. So I'll thank you very much for your attention. Thank you.
Thank you for the presentation, Dave. We will now be moving on to the Q&A session of this event. So we will now be taking questions in the chat, so please feel free to enter any queries you may have. To start off, we received a pre-submitted questions from one of our attendees. So how does this compare to what's on top of the UK mountains, say Ben Nevis, for example?
Yeah, okay, Ben Nevis. So Ben Nevis is a different sort of mountain. It's made up of a granite. I think the granite's probably about 350 million years old. I'm not quite sure. But the granite would have been intruded into the Earth's crust. It would have punched its way up through the crust to form this particular feature. So basically, when we're building mountains, a lot of it is due to collision, and it will depend on the particular rock types that are involved in the collisional event. And often it's associated with what we call intrusions, which are due to magmatism in the Earth's crust that may or may not be associated with the mountain building episode. So if we look around Britain and Ireland, the various mountain belts are built of different types of rocks, of different types of ages, depending on when these collisional events took place. So, you know, if you go into the Pennines, you'll see the mountains are all limestone. If you go to North Wales, they're all Cambrian slates or sandstones or those sorts of things. Thank you.
Thank you, Dave. So we have another question asking, what sparked your interest in geology? Did you always wish to follow this route, work in the field and travel?
Well, I did actually. So I went to secondary school not very far from here, a place called Walbottle Grammar School, which doesn't exist anymore. And we had a rather inspiring chemistry teacher, Mr. Brooks. And he started a rock club, and I was sort of very interested in minerals and rocks at the time, where we used to meet after school, and we go out into the Pennines and collect minerals in Weardale and things like that. And I started getting a real interest in fossils too at that particular stage, and took an O-level in geology, which was quite difficult to do at the time because we did it on our own, and then went off to Imperial College to study geology, and then I became really fascinated with fossils. And I think the traveling aspect too, I think it's really important, as I mentioned earlier, to link up with international networks. But it's also very exciting to visit colleagues in different cultures, in different geological settings, but learn a lot about their research, but also the way that they do research and the way that they think about research. And I think it's a very stimulating way to work, and we get many new ideas out of these networks.
It's very interesting that you mentioned culture. So upon visiting such a wide range of different cultures to carry your various expeditions, do you think that you encountered any instances of cultural shock?
Cultural shock?
Yeah.
Not really. I think one thing I would emphasize, and the sort of this question comes up, culture, politics, those sorts of things pops up every now and again. I think we have to always remember that we're scientists, we're not politicians, and we've probably known each other quite a long time in our various networks, our various groups. We've been on visits together, which initially, when you get to know people, you not only start writing papers together, visiting localities together, but you do a lot of cultural things. And I've never had a cultural shock, but I've been very much aware that people think differently, do things differently, and that's part of the diversity of our research networks, and that makes it all the richer.
We've received another question asking, is the gradient between your rocks at 5,000 meters and those near 8,800 meters altitude of recent post-Indian collision origin?
Well, I think not to answer the question, but to try and illustrate the question, you know, the Everest range is rising. It's continued to rise. And so there are sort of isostatic effects in which the mountain chain is buoyant and is building up. I think it's a very difficult question to answer as to the history of elevation of these mountain ranges. It can be done. There are various means of actually doing it, but we've not got involved in that research. I think we were content to, as paleontologists and sedimentologists, to look more closely at the rocks themselves and try and reconstruct the paleo environments and the ecosystem that existed back in the middle part of the Ordovician.
Thank you, Dave, for your answer. So how do you think your expeditions will change after the pandemic, and is there anywhere you aspire to explore?
Yeah, I think that there's absolutely no doubt about it. The pandemic has stopped a lot of field work and geological field research. The background I put on today is from the Beatic Mountains, and I very much enjoyed co-leading student field trips there, second year field trips from Durham University over quite a number of years. And the students gained some fantastic field experience from basically mapping a lot of this particular terrain and just generally being out in the field and making field observations and interpretations. I think a lot of colleagues, and I know through the International Commission of Stratigraphy, a lot of colleagues' field campaigns have halted. And there's a lot of plans again to open up, but I think it will be quite slow. We really don't know what the trajectory is at the moment. And certainly I've got quite a number of plans. There's number of networks and colleagues I'm now going to work with, a couple of places I haven't been before, and to continue this research on Cambrian Ordovician geology.
So speaking of your experiences at Durham, do you think there's anything that pops out to you the most during your time here in terms of field work?
Yeah, I think I don't want to be too negative about it, but being college head, and I remember when I was interviewed for the job by the Vice Chancellor, and we had a very interesting talk about various things. And then just at the end, he said, well, you'll have time for research, no problem, but you won't be dashing off to Greenland anymore. And I sort of realized that as a college head, you simply cannot be away for any length of time. And so the days of the field expeditions to various parts of the world where it might be a couple of months that you're gone for was not realistic in the position of being a college head. Nevertheless, I have been able to do a fair bit, and fortunately I've got a very good team behind me in Van Mildert, Deputy Principal Vicky and colleagues that can cover for me over shorter periods of time. And so some of the work I've been able to do in Morocco and in Siberia and visits to museums in the States and shorter visits to colleagues in France and Belgium and Scandinavia, these have been possible. And so I don't think I've lost a huge amount of momentum in my research, but I think for somebody that was used to a lot of field geology and being away from home, it's you had to adapt to a different strategy.
Thank you, Dave, for your answers. We've received a couple of compliments about your talk, saying that it was very informative and very interesting. So thank you very much for your time. So we've now come to the end of all of our questions. If anyone has any last minute questions, please feel free to pop them in the chat. And yeah, thank you, Dave, for the talk. It was very lovely and interesting to hear about your experiences. And thank you everyone for joining us today. We really appreciate everyone's support.